Okay, so this presentation, the discussion about this presentation will focus on some very pragmatic and realistic ways that we can take very complex codes and optimize the execution time or the cost or both when we run them on the cloud. So it's a long title. It's just also a summary of the work, So a little bit what I'm going to talk about, what is the problem background and the objectives we're trying to accomplish. Then I will go through quickly over the method, the highlights of the method. How do we decide how to run these complex codes, in an environment very consisting of multiple different CPUs and GPUs. And then I will give you specific examples, what we did exactly with actual models that are being used in this field. I will give you 4 if we have time. Actually, this transparencies at the very end includes many more models to just show you, how easy it was for us, straightforward, or, so that we can analyze all kinds of different models, and then some conclusions and reference and so on. So what is the objective and what is the problem trying to solve? Of course, we are trying to have a realistic and practical way to minimize the execution time of complex codes that when they run on the cloud, a cloud environment, and also minimize the cost. So because you don't want to keep paying for running inefficient code, you want to also get the results and the value out of running these models as quickly as possible. Secondarily, you want to, when this code actually, let me focus first a little bit. So when wall clock time or execution time optimization, we want to have multiple targets, hardware targets, different CPUs, different vendors, the AMD, Intel, different generations, different configurations of this environment with different capabilities. Also, we want to be able to run at extreme scales, or at least evaluate code that runs at extreme scale, thousands of cores, or hundreds of GPUs, or thousands of GPUs. And we want to be able to build this environment, these systems, using different kinds of compilers, GNU, Clang, and different MPI, Intel MPI, Open MPI, and different libraries, math libraries, etc. And the environment that we are focusing on is Azure, which we will see it as our HPC compute environment. What are the target applications are quite complex multi-physics couple model codes that actually are under continuous development. This means that we add code or change code, add solvers, or the developers, they keep adding new capabilities. So you have to keep building and testing this. And at the same time, so it's a very dynamically varying environment. So the challenges is to be able to build quickly, build in different ways, using different optimization methods, different compilers, different MPI stacks, etc. And of course, this I have extreme scalability objectives, thousands of MPI ranks, and we'll be able to use different CPUs and GPUs. And one key characteristic, they have multi-level parallelism. That is, they have MPI and or threading, like through OpenMP, or MPI plus OpenMP, and some GPU acceleration. So there are at least 2 levels of parallelism. And we'll exploit this to find out the best way to run this on different kinds of systems. Also, it's very hard to predetermine the performance of the code by just looking at the code. And different models and different target hardware have completely different performance. So the best way to find out how these codes perform is to run them on the actual environment using actual models. And this is what we're going to do here. The example application is called GEOS, and GEOS is a very large, fully coupled multi-physics simulation framework for combines geomechanics, fluid flow, and CO2 and hydrogen storage, geothermal, faults, and shale and tide fracturing. So it's a very complex code, dynamically varying. We have people from different disciplines adding different physics solvers, and then we have people that change or add capability with the linear solvers that are behind, have to be used when we solve the system. This can simulate, GEOS can simulate up to, say, in the order of billions of cells, or the mesh can be billions of cells in size. It can run, different CPUs and GPUs. It uses several components that came out of the exascale computing project, like Raja, Chai, Ampere. And these are components that are designed to be for exascale environments. So you want to be able to run at very large scales and in environments with extreme capabilities, acceleration, etc. So this is, and GEOS has been developed currently by the FC Maelstrom Consortium, which is Lawrence Livermore National Labs. They have done most of the work, but also with addition from Total Energies, Stanford University, and Chevron recently. So they have references there. If you want, you can go check out some background on this. Quickly, I want to highlight how do we go about figuring out how to run these codes, these complex codes, as fast as possible, or with minimum cost in the cloud. Now, when I talk about cost, okay, first of all, execution, wall clock time. This is the time lapse between the time you launch the code until the time it terminates. Okay, that's the total execution time. And the cost is the amount of resources you use, in this case, the amount of number of nodes you use, times the cost per node per unit time, times the wall clock time. So the shortest execution time will not necessarily yield the cheapest time, okay, or the lowest, and vice versa. So we have to sort all these possibilities. So what we do, we have built in this framework, I call it Chevron Performance Scalability Analysis Framework, that evaluates the code in different selected runtime configuration points. So an RTC is an tuple that contains this information basically to characterize how I run the code. H is the type of the model, the hardware model, AMD CPU or some GPU, and actually how many cores you have, how much memory, etc., and L3 cache and all this. Then also how many total threads I want the code to have. And the thread is the product, the number of MPI ranks times number of threads per rank. And how many nodes I want to let this system use. So this is one, and also some other items like what compiler I used, what options I used to build this. Okay, so it can include all kinds of configuration points. Now this will become the x-axis, and then while I will run the code, I will profile it, and I will collect, this kind of information at a minimum, wall clock time, some initialization time, the time to solve the linear system, and this is if it executes on the GPU. This is actually exclusively run on the GPU. Setup time is the time to prepare the matrices before each nonlinear step, and this can sometimes may take a lot of time, so we have to pay attention there. And also total time spent on MPI. So this will become here the x-axis on the graphs I'll show you, and this here will be on the y-axis. Now, you can say, but these are so many evaluation points, so I cannot evaluate all these. I will spend a lot of resources. So there is a heuristic by which, first of all, we collect hardware information based on the hardware model, which tells us how many cores we have, how many sockets, how many memory domains, what's the size of the L3 cache, and then we make some decision how to run the code, how to select these evaluation points, these runtime configurations, in a way that we know will have better performance. Instead of going through the entire space, we just use heuristically, we reduce the evaluation space drastically. So what happens, let me give you a small example. When I have, say, 10 nodes of which 120 cores each, then I have 1,200 cores. So, but what I will do, I will evaluate, I will launch, say, from 1,600 to 1,200. Minimum number of cores to maximum number of cores will be half of the number of physical cores to all the cores being used. And I will select different number of ranks, a number of threads per rank to evaluate the system. And I will collect this profiling information. And then Finally, after I go through this sequence of runtime configuration points, I will identify this is the minimum cost and this is the minimum execution time. But I'm not exhaustively going through the entire space. And so it's very important to place the ranks and the threads in a particular location on the system. And from experimentation and practice, we know it plays a big difference, how you locate. So this analysis environment selects interesting or nice places to put the ranks and the cores, so we know we can guarantee we start from a good starting point. And then we continue some evaluation until we locate some minimal, not minimum, something which is close to a minimum, but maybe not absolute minimum. Finally, we will generate strong scaling curves. What this means is that you solve the same problem, but you increase the number of resources. And then you identify what is the resource configuration that minimizes cost or time. So this is semi-automated method and avoids brute force evaluation. And once we have the best way to run the code on different types of environments, then we can go in and do in-depth profiling of the code there and fix items like, okay, MPI is too expensive here, or the linear solver didn't perform well, or I have to keep recreating the matrices. So we can do more detailed profiling and optimization. So anyway, the utility, again, we run the problems and we get results as fast as possible or at the cheapest point as possible. And we can, then, because we run them with minimum resources, we can run larger models and so on. So this is, we can discuss later if there is time. So I want to quickly go and show you, this is the SimCO2 model that, oops, I'm sorry. You can read here what's about. It's basically CO2 sequestration and storage simulation of the subsurface formations. So this is an actual model. It's very popular because it's trying to simulate how the CO2, once we inject it in the reservoirs, how the CO2 after 100 years, 50 years, 200 years, how it's going to stay or move around this the reservoir. And it's used for people who want to sequester CO2 and they want to know how this reservoir, particular reservoir, will behave, as time progresses. So it's something valuable for people trying to, to store CO2. This is a very difficult code because it includes several solvers together. It's called multi-phase poromechanics with wells. So it has fluid flow, it has geomechanics, it has a lot of nonlinear and physics solvers that have to collaborate and solve coupled systems. So it places very large demand on the hardware resources of the system. So let me show you quickly what, here there were some experiments. Actually, this is a summary of experiments on Zen 4s and on Zen 3s. These have 120 cores per node. These have 176. So by going through this directed and selective way to evaluate this geos running this model, we found out, okay, the top curve is the wall clock time. And we found out that if I use 2 nodes with 4 threads per MPI rank and total 352 threads, so you can see how many ranks I have, okay? This is the best way to run this model on Zen 4, and this is the best way to run it on Zen 3. And as you can see, absolutely the Zen 4 runs better, this model, versus using Zen 3. So as I mentioned to you, the x-axis includes the configuration points. So the very top row is total number of active threads in the code. The next row is number of threads per MPI rank. And the bottom row is how many nodes of this type we used. So immediately here, we found, using selective evaluation of the RTCs, what is the fastest way to run it. And now, the top curve is the total execution time. The red curve is actually time to solve the linear system, and this has to do with how much time, effort the linear solver spent to produce results inside the nonlinear iterations. As you can see, most of the time is spent there, but also let's see something here. This dashed line is actually time spent in MPI. So based on how many MPI ranks you have, etc., you can see you may start spending quite some time just doing MPI. So this is not compute, okay? This is pure overhead. So we can go back and evaluate why the MPI implementation in this code behaves this way. So you can see this uses a lot of broadcast, a lot of reduction operations, non-blocking operations. But then you can go back and see, okay, I was waiting so much time to finish the reduction, or it's doing a lot of non-blocking calls. And there's a lot of MPI probe to see, okay, I want to see, did it finish? Did the MPI communication finish? So these are the things we can go back and optimize. And of course, it makes sense to optimize the code that operates at the optimal point. You don't want to optimize the code here because you can already get something much better. So first you identify the best configuration, then you go in and you optimize the internals of the code, data structures and communication, etc. So I know this is a very busy, it's a very busy slide, a lot of things, but basically it's total execution time, time to solve linear system, the MPI time, and something called the setup time right here. Setup time is time spent before each nonlinear iteration to prepare the matrices for the next step. So this is also something, people, as you can see, starts taking quite some time. And so this is something we can optimize. Any questions so far about this? Okay, so let's proceed. So this is the execution time. How about the cost? We cannot show you exact figures of how much exactly time we spend. This is exactly the same experiments, but now this green curve is how much money we spent to run it on Azure. And now this is actually the cheapest way to run it on Azure. Still 2 nodes, Zen 4 with actually 1 thread per rank and 352 ranks. Okay. And this is the minimum cost time. And as you can see, so this is the Zen 4 experiments, actually a summary of them, and this is a summary of the Zen 3 experiments. So Zen 4, which is cost per unit much more than the Zen 3, still yielded better results, cost results, than using a cheaper unit. So because different number of ranks and different number of OpenMP threads per rank and different number of configurations gives you different cost point and different execution time, and this application is not easy by looking at the code to tell, okay, this is how I run it. It's going to be the best way. So this method gives you a very streamlined way to identify from the cheapest to the fastest method and everything in between. So actually, this is a spectrum of performance versus cost values. And let me go one second, I didn't mention this. So how much time did we save? Well, the difference between the worst and the best execution time was 61%. So if we're running these models, this particular model, many times, the cost saving can be up to 60, almost 61%, 62%. And based on the different configurations we tested, the average savings were 42%. So if you run this kind of models thousands of times or hundreds of times, then you can save quite some time in the long run. Okay. Next, the cost. The cost savings we had, almost 78%, on the average 62%. So this is a good, you can get some quite nice savings, if you go this way. So here we're trying to correlate total monetary cost versus execution time. So this is, it's a Pareto chart. On the y-axis total cost, y-axis the wall clock time, x-axis total cost. Now the points here is operating points that correspond to this x-axis here. So it makes sense to run this code down at this level. Now we cannot see exactly here the configurations. If we had an actual, non-graphics, environment, we can go here and see, the cursor and see exactly which configuration is it. But this to demonstrate that if we run down here with these configurations, we tend to minimize total cost and tend to minimize total execution time. So this is the desired area we want to run on. If you are running somewhere here, you're wasting time or money. So that's the gist of it. Now, very quickly, this is another model. This is GPU only. Actually, this is A100 and H200. This is the Grace Hopper. So this is similar experiments, but this purely on GPU. And we did with the Grace Hopper. Actually, performance was better than 4 A100 GPUs for this particular model. And actually, this is also quite, it's a coupled physics model, etc. So based on the cost, you may be able to save a lot of money, if you run at this point. Let me quickly, so this same model, we run it for A100s GPUs. Of course, the Grace Hopper I showed you, also Zen 3, Zen 4, and some Sapphire Rapids. And the best configuration was still, again, Zen 4, this particular configuration. These boxes here show you how many GPUs I used. Of course, for the CPU, we don't have GPUs, so GPU is 0. And here shows you exactly, how the best way to run it again. The GPU workload time savings, the A100s versus the Grace Hopper was 71 and 49, the average, and the CPU workload time savings was 82 and 63, respectively. So, there is a similar discussion about the cost. Again, the best cost we figured out was using Zen 4s. This is actually, we are calculating here using the A100 nodes on Azure. So again, the Zen 4 proven to be better. So again, similar Pareto chart for these experiments. If you run somewhere down here, you are doing okay. If you're out here, you're wasting money. So this is the gist of the method and the different, you apply different models and different hardware to identify this spectrum of performance versus cost. That's basically another model, SP11B. It's very complex. This is weak scaling. So we increase the problem size, then we throw in more hardware and see how it performs. Just throw in there, And actually, now the last thing I want to talk about, this is GPU performance comparing A100s and the MI250X. This will run on the Frontier, which was the first exascale system, 2024. So, but our experiments we ran just on our, humble Azure environment, and we managed to get actually slightly better performance. So this is pairs, okay? This is when we run it on Chevron. This is when actually numbers reported by, did I put this? Okay, these people, these are from Lawrence Livermore. They run on Frontier, very large experiments. And we ran the first 4 levels for weak scaling, and we did pretty well everywhere, except now we used up to 256 GPUs, I believe. So we did, a little bit better, than there. But beyond that point, we noticed that MPI started becoming a bottleneck for us, and then Frontier, which is a very highly tuned and very well-defined, system with very, very, extensive communication fabric, very capable communication fabric. Then it started doing better because basically communication was the issue. So these are the highlights of the methods, are examples. And if you guys have any questions or any blame or any kudos or any.
So are there any questions for Michael? So I have a question. How difficult was it to build these applications for the different architectures compared to your traditional applications?
Yeah, this code particularly, it's an accumulation of many subsystems that came out of national labs, linear solvers, Raja, all kinds of different layers of. So it is. It uses thousands of CMake file scripts just to build the dependencies and also the code itself. It takes hours to build. So it's a quite a difficult and annoying environment to build. So at Chevron, we created some framework where we can specify this is how I want to build with these compilers, these options, blah, blah, etc. Use Intel MPI or OpenMPI. And then, there is this framework builds everything for them, hides details of our environment. And then, they can execute exactly the same configuration that it was built with, by just using a simple initialization script. But it was quite tedious. And,
well, thank you, Michael.
Thank you.
Thank you. I just had a quick question. I was kind of, I don't work for AMD or Intel, but I was kind of interested to see the Zen 4 versus the Sapphire Rapids, and curious why, I guess HBM didn't buy you as much because of all the different things going on, or was it the big caches in the AMD, or?
The Zen 3 is using the high L3, high bandwidth L3. And but still, Zen 4, it didn't use that. This is the plain model, the 4 megabytes per core L3. Because yes, exactly, the HBM on the Sapphire Rapids, the units we used, that was the test unit that was given to us. The HBM was much smaller, so it was not so easy to exploit it. If you have much more of that, or if you are able to, you have to go inside the code and say, this goes to HBM, this does not go. So this becomes, with the AMD architecture, you place the threads wherever you think is the best place, and then you can extract the maximum bandwidth out of the memory, and also capacity out of the L3 cache. And the reason we do so well on the AMDs is because we can use the level 3 cache much more efficiently and more effectively.